Hello, welcome to this lecture. So in this lecture, we'll learn about fundamental group. So this fundamental group will be useful to find non-elementary fusion groups. So our next goal will be to prove that fundamental group of closed orientable surface of genus greater than or equals to 2 are fusion groups. And in fact, they are non-elementary fusion groups. Okay, so let us begin. Okay, so to understand fundamental group, so we need to know, so what do you mean by path homotopic? So let us begin with a topological space X, and let us take two paths. So what do you mean by paths? So these are just continuous map from the closed interval 0, 1 to your X. So let us take two paths, alpha and beta. So these are just continuous maps from this closed interval 0, 1 to X. So joining same pair of points x0, y0 in X. So these two paths, alpha, beta, are said to be path homotopic to each other if there exists a continuous map H from this unit square, so closed interval 0, 1 cross closed interval 0, 1 to X. So if there exists a continuous map capital H from this square to X such that H s comma 0 is alpha s, H of s comma 1 is equal to your beta s. And for each t, so H0t is equal to x0 and H1t is equal to your y0. So this second space interval, closed interval 0, 1, you can call it to be time parameter. So at time t equals to 0, so H, that means H s comma 0, it is the path alpha. And at time t equals to 1, H s comma 1, it is equal to beta s, that is the path beta. And for each time t, so H of 0t, so that homotopy is fixed, so that is equal to your x0. And at the other end, H1 comma t, so that is equal to y0. Okay. So if I draw a picture, so this is the schematic diagram of this homotopy. So this H, it is called the path homotopy. So we have this unit square here, and at the bottom, so here, so H s comma 0 is alpha, so I have just written alpha here, and at the top, H s comma 1 is your beta, so that's why I have written beta here. And in the left side here, H0, so H of 0t is constant x0, so that's why I have written this x0 here. And H1 comma t, so this is in the other side of the square, it is equal to your constant thing y0. So therefore, so if I take the image, so this is in the space X. So yeah, so this inside part of the square is mapped to here, suppose. So there's the picture of alpha homotopic to beta. Okay, so next, what you can prove that if alpha is path homotopic to alpha prime and beta is path homotopic to beta prime, and suppose this concatenation here, so this alpha star, so this alpha and then beta, so endpoint of alpha is the same as the initial point of this beta, and the terminal point of alpha prime is same as the initial point of this beta prime. Yeah. So what is this? What we are assuming here? So suppose alpha of 1 is equal to your beta 0, and alpha prime 1 is equal to your beta prime 0. So then what is the meaning of this concatenation? So this I'm sure that you have seen in the algebraic topology class. So alpha star beta of S. So this will be, so this is equal to alpha twice S if S is lying in the interval 0 to half, and it is equal to beta 2S minus 1 if half is less than equals to S less than equals to 1. So this is the definition of this alpha star beta. Similarly, you can define alpha prime star beta prime. And now what is the result? If alpha is homotopic to alpha prime and beta is homotopic to beta prime, so then one can prove that this alpha star beta is path homotopic to alpha prime star beta prime. So this notation, it means that so alpha related to beta means that alpha is path homotopic to beta. So one can check that, so this relation, this is an equivalence relation on the set of all paths between 2 points x0 and y0. So now if I take this set, so omega x0 y0, so this is the set of all paths between x0 and y0, and I put this relation on the set. So this is an equivalence relation on the set, and the square bracket alpha, so this will denote the equivalence class containing alpha. And yeah, so because of this fact, this fact, so one can check that, so this binary operation, so if I take two paths alpha and beta such that alpha 1 is equal to beta naught, so you can, this concatenation makes sense. So this gives you a binary composition on this omega. So this binary composition you can extend into this quotient space. So that is the thing I have written here. So square bracket alpha star square bracket beta means the equivalence class of this alpha star beta. So this, in fact, it is a well-defined thing. This composition is well-defined. So this makes sense. And also, we have this property of associativity. So now suppose I take three paths, alpha, beta, gamma, from x0 to y0. So then, so first what I'll do, I'll first do this beta star gamma, and then concatenate alpha with this beta star gamma. And in the second thing, so I'll concatenate alpha with beta, and after that I will concatenate this alpha star beta with your gamma. So both will give the same element in the quotient space. So this is my definition. So this is my definition. So alpha star beta star gamma, this turns out to be this thing. So alpha twice S is varying from 0 to half, and beta star gamma up to S minus 1, where S is varying from half to 1. And now if I expand this thing, yeah, so if I expand this thing, so it turns out that, so alpha star beta star gamma is nothing but alpha to S. S is varying from again 0 to half. So I'm expanding then again this beta star gamma. So that can be written like this. So beta of 4S minus 2. So S is varying from half to 3 by 4. and then equal to your gamma 4s minus 3. S is varying from 3 by 4 to 1. So similarly, so I have an expression for this alpha star beta star gamma s. So note that, so we have now two paths. So one is your alpha star beta star gamma, and another one is alpha star beta star gamma. So we have two paths. So this closed interval 0, 1 to x, and again this is a map from this closed interval 0, 1 to x. So these are continuous maps. So image of these two maps are same. So only the difference is in the parameterization. Yeah. Now, so these two parameterization, so they are path homotopic to each other. So what is the homotopy? So this will give you the homotopy. So you can draw this picture here. So you take this unit square. So you take this unit square, and at the bottom, so you have this alpha star or beta star gamma, and then at the top you have alpha star beta star gamma. And now to get the homotopy, so what you do, so you join this half comma 0 point to 1 by 4 comma 1 point by a straight line, and also join this 3 by 4 0 comma point to this half comma 1 point by again a straight line. And now what you do, so you take any this line segment, horizontal line segment, and now note that, so this point here, so this intersection point, so the coordinate of this point is 2 minus t by 4 comma t. So s is varying from this. So s is varying from 0 to 2 minus t by 4. And so therefore, so this 4s by 2 minus t, it lies in the closed interval 0, 1. And I just define alpha on that thing. So alpha of 4s by 2 minus t. Similarly, here also for the other part, so you can define this beta. And in the next part, using the equation of the line segment, you can define gamma here, gamma on this horizontal line segment. So we have this thing. So this is my definition of this capital H. And now you can check that at time t equals to 0, so Hs comma 0, it will give you the path alpha star of beta star gamma. And at time t equals to 1, Hs comma 1, it is nothing but alpha star beta, and then you concatenate with gamma. So therefore, so these two elements are same in the quotient space. Okay, so our goal is to define the fundamental group. Yeah, so in the group, we need an identity element. To produce that identity element, so we'll be needing this constant map. So let's see why not with this constant map. So taking the value y naught. So see y naught s is equal to your y naught for all s belongs to this closed interval 0, 1. So now the claim is that, So alpha star cy naught is path homotopic to your alpha. So alpha is a path, cy naught it is a constant path. So alpha star cy naught it makes sense. So alpha it is a path from x naught to y naught. So therefore this makes sense, alpha star cy naught. And again, image of this path is same as the image of alpha. So only the difference is in the parameterization. So now again, how to get the homotopy? So what you do, so you take this unit square and join this half comma 0 to this 1 point by a straight line. So equation of this straight line is s equals to t plus 1 by 2. So again, you do the same thing here. You take the horizontal line segment. So s is varying from, so here this s is varying from 0 to t plus 1 by 2. So therefore, in this interval, so we define h to be alpha 2s by t plus 1, and rest of the thing it is y naught. So here it is your y naught, and here, so here you are getting this image, you are getting this alpha. Yeah, so h s comma t is equal to y naught if s is varying from this t plus 1 by 2 to your 1. So this gives you a homotopy between alpha star cy naught and alpha. So therefore, so this two things in the quotient space are same. So you take the equivalence class alpha star equivalence class cy naught is equal to the equivalence class alpha. Similarly, if I take the constant map cx naught, so this equivalence class of cx naught star equivalence class of alpha is equal to the equivalence class of alpha. And now, if I take any path alpha, so I can define this alpha bar, which will give you the inverse of this alpha in the fundamental proof. So alpha bar s is just defined to be alpha 1 minus s. So alpha bar 0 is equal to your alpha 1, which is equal to y naught, and alpha bar 1 is equal to alpha naught equal to your x naught. Yeah. So alpha we can think in this way. So alpha is starting from x naught and ending at y naught, and alpha bar is the reverse of this alpha. It is starting from this y naught and ending at x naught. Okay. So next, what we can prove that, so this alpha star alpha bar, so this is a loop based at x naught. So it is starting from x naught and ending at x naught. So this alpha star alpha bar, it is starting from x naught and ending at x naught. So the claim is this path is path homotopic to the constant map cx naught. So again, the proof is simple. So what you do, so you travel, so the thing is the following. So the philosophy is the following. So you travel up to alpha 1 minus t, and again you come back. So this will give you the homotopy. So at any time t, so what is the path? So you go there and again come back. So that is my path. So that will give you the homotopy. So you can write explicitly the homotopy. So h s comma t is alpha to s. S is varying from this 0 to 1 minus t by 2. And h s comma t is the constant map. So what is the constant map? The constant map alpha 1 minus t. So in this interval, so hs comma t is constant, and that is equal to alpha 1 minus t. And again, when s is varying from 1 plus t by 2 to 1, so we take alpha bar to s minus 1. So this will give you the homotopy. So this following homotopy, alpha bar star alpha is path homotopic to your cy. Sorry, so this it will give you the homotopy. This homotopy, alpha star alpha bar is homotopic to your cx naught. Similarly, you can prove that alpha bar star alpha is path homotopic to cy naught. So again, we have these two equations. So now let us come to the definition of this fundamental group. So let X be a topological space, and let us fix a point x naught belongs to your capital X. So this omega x naught, it is the set of all paths or loops at x naught such that, so this alpha 0 is equal to alpha 1 is equal to x naught. So by loop, what do I mean? So a loop is a continuous map from the closed interval 0, 1 to your x, and at the end points, it remains the same point x naught. And now what is the definition of this pi 1 x naught? So it is this quotient space. So omega x naught. So take the equivalence class of all loops. Yeah, so this quotient space. So whatever we have done, so earlier here, so now this y naught is equal to your x naught. So alpha bar, so this will be inverse of your alpha, and this equivalence class of this constant map cx naught. So this will be an identity map because of this thing, because of this. So therefore, so what we have shown that, so this pi 1 x naught with respect to this composition forms a group, and it is called the fundamental group of x based at the point x naught. Okay. So if I take x to be your Rn, so Rn, it is a convex space. So if I take any x naught, and if I take any x point, I can join this x naught to x by a straight line. So if I take this homotopy, hx comma t is 1 minus t x plus tx naught. So this is called the straight line homotopy. So this will prove that this fundamental group of Rn is trivial. So now we have the definition of this simply connected space. So a path connected space X is said to be simply connected if its fundamental group pi 1 x is trivial. So in the definition of simply connected space, we start with a path connected space, and if the fundamental group is trivial, then we call that space to be simply connected. So now note this basic fact that, so if I take a path connected space X, and if I take 2 points x naught and x naught prime, so then the fundamental group of x at x naught and the fundamental group of x at x naught prime, so those two groups are isomorphic to each other. So that is a very standard result in this basic algebraic topology. Okay, now what is an example of simply connected space? So what I said, this fundamental group of Rn, it is trivial, it is a path connected space. So Rn is simply connected space, and also we can prove that if I take any Sn, or let us take S2. So S2 is simply connected because its fundamental group is trivial. Or if I take Sn, this unit pair where n is greater than or equals to 2, pi 1 of Sn is trivial. So Sn is simply connected if and only if n is greater than or equals to 2. So now let me come to this theorem. So this theorem is about group acting on a simply connected space. So let me give you the reference for this theorem. So this you can get in Armstrong. So what this theorem is telling, so let G be a group acting on a simply connected space X by homeomorphisms. And suppose for each element X, there exists an open set Ux such that, so this X is contained in this open set and G dot Ux intersection Ux is empty for all non-identity element G. So this group G is acting on, so this group G is acting on the space X. And for fx G, this element, so this map is a homeomorphism. So this we have assumed. And we have also this assumption that if I take any non-identity element G, so G dot Ux, it makes sense. So G dot Ux intersection Ux is empty. So then the claim is the fundamental group of this quotient space. So X mod G, it is the set of all odd bits. So fundamental group of X mod G is isomorphic to G. Yeah. So this is the result. So this you prove using covering space theory. So I'm not going to the proof. Maybe in algebraic topology course you have seen this thing. So we are going to apply this result in our context. Okay, so for example, so if I take this group Zn, so it is acting on this Rn by translation. So this is my action. So it is acting on Rn by translation. So by this, so Rn, it is a simply connected space, and you can check that. So this group Zn satisfies this property, so it is not very hard to show that thing. So therefore, the fundamental group of Rn mod Zn is isomorphic to your Zn. And what is this Rn mod Zn? It is homeomorphic to S1 cross S1 cross S1 up to n times. So this is basically your n torus. Okay. So now let me tell you this fact. So this will be proving later. So let us take this group generated by A1, B1, A2, B2, AG, BG, and the product of this commutator is equal to 1. So what do you mean by commutator? So commutator stands for the square bracket AI, BI. So this is equal to AI, BI times AI inverse times BI inverse. So this group, it acts properly discontinuously by isometries on the unit disk with hyperbolic metric. So this group, So in some class we'll prove that. So this group acts properly discontinuously by isometries on the hyperbolic plane, or you can take the unit disk model of the hyperbolic plane. So this action is properly discontinuous. So from that you can prove that, so this action will satisfy this property. So this action will satisfy this property. So the action is properly discontinuous. From that thing we can prove that that action will satisfy this property, and therefore from that theorem, so the fundamental group of the quotient space is isomorphic to this group. And again, so this quotient space is nothing but is homeomorphic to closed orientable surface of genus G, where this G is greater than equals to 2. So this will prove that, so because this group is acting on this hyperbolic plane properly discontinuously, so this will prove that this group is Gaussian group, and this is nothing but the fundamental group of closed orientable surface of genus G, where this G is greater than equals to 2. So I'll be proving this thing. So this group acts properly discontinuously by isometries on unit disk with hyperbolic metric in some class. That requires a proof.